We'll start in 1 minute. Today we'll be in Chapter 8, Section 1 on simplifying expressions with roots. This symbol is called a radical sign. The number or algebraic expression inside the radical is called the radicand. For example, the radicand of this radical with 7 inside is 7. The radicand of this one is x. So in general, if n is a positive integer, then the symbol, it's the radical sign, and the integer n is right there. That's called the index of the radical, or a radical sign with index n. So n is a positive integer. When the index of a radical is n equals 2, then the radical sign with a 2 or with no number or no integer at all is called a square root. Or a radical sign with index 2. So to reiterate, if the index n of a radical is not written, then it is understood that the index is n equals 2. So the radical sign with no index is equivalent to the radical sign with index 2. Each of those means square root. So I'll jot here that a radical with index 2 is a square root. So a little bit later, I'll expound a little on the term square root. Okay, if we let capital A be a number, then this expression is referred to as the principal square root of A. The principal square root of A is also the positive square root of A. How do we know that it's positive? Well, there's not a negative sign in front of the radical, so it's the positive square root of A, or principal square root of A. Those are synonymous. But the square root of A, the principal square root of A, is equal to the number whose square is A. When you square something, you raise it to the second power. So that is, if the principal square root of a is equal to m, then the number a is equal to m squared, m to the second power. Okay, if you are familiar with perfect square whole numbers, that will be very useful. So let's review the perfect square whole numbers. The perfect square whole numbers are found by squaring whole numbers. Square roots of perfect square whole numbers simplify to whole numbers. Okay, here's an example. The principal square root of 49 is equal to 7. We know that's true because 7 to the second power equals 49. 49 is one of the perfect square whole numbers. We know it's a perfect square whole number because 49 is the result of squaring the whole number 7. Okay, so as I've already mentioned, being familiar with lots of perfect square whole numbers will be useful, or they will come in handy. So here's a short list. The entire list is infinitely long. So this is relatively short compared to an infinite number. So if you go all the way to 900, what number would you square to get 900? Yeah, 30. 900 is 30 to the second power, or 30 squared. So if you can work on remembering or memorizing those perfect square whole numbers, that will be to your advantage. So 30 is not a very big number, and 30 to the second power equals 900. So numbers, perfect squares smaller than 900 will have square roots that are between 1 and 30. So they won't be too hard to find, even if you don't memorize them. Okay, we'll evaluate or simplify some square roots. This first one on the left, the square root of 25. We don't always have to say principal square root, but just remember that it's a positive square root. The square root of 25 is equal to the number that you would have to square to get 25. So the square root of 25 is 5, because 5 to the second power equals 25. The square root of 169, yeah, that's 13, because 13 to the second power equals 169. The square root of 289, another fairly simple square root to remember is the square root of 400. The square root of 400 is 20. So if 289 is a perfect square, then the square root of 289 has to be less than 20. So you can look at numbers less than 20. These are just examples of square roots of perfect squares. The principal square root of 289 is 17, because 17 to the second power is 289. And the square root of 361 Well, if 361 is a perfect square, and it is a perfect square, it has to be less than 20 because the square root of 400 is 20, and 361 is less than 400. So this one is 19. I'll mention something that you might want to do. You might not want to do it either. But there's a way you can mentally or in your head square integers. So for example, if you want to square 19 in your head, how can you do it? Well, you can think of 19 times 19 as, in your mind, you can think of that as 10 plus 9 times 10 plus 9. So in your head, think of, okay, I have 10 plus 9 times 10 plus 9. First, I multiply 10 times 10, which is 100. And then I'm going to add 10 times 9 twice. So plus, I'll just write plus 9 times 10 plus 9 times 10. And then after that, I'm going to add 9 times 9. With some practice, you can get pretty good at squaring whole numbers in your head. You just have to keep track of those four numbers and then add them together. But the numbers are pretty easy to add. 10 times 10 is 100. Plus 90, I'm up to 190. Then I add 90 again, I get up to how much? So 100 plus 90 and then plus 90, I'm at 280. And 280 plus 81 is 361. Okay, moving on. Note that the principal square root of negative 100 is not a real number. The reason is there is no real number whose square is negative 100. So anytime you see a square root of a negative, just keep in mind that it's not a real number. Okay, by definition, the square root of negative 100 equals m if m to the second power equals negative 100. So m is not a real number because if you square a real number, you never get a negative number as a result. One thing that you should remember, though, the square root of negative 100 is a number. It's a certain kind of number. It's just not a real number. A little bit later this semester, we will learn we will learn about square roots of negative numbers and what kind of numbers they are. They're just not real numbers. Okay, a formal definition of the square root. If we let x be a real number, then the square root of x to the second is equal to the absolute value of x. Okay, so note that in this definition, x can be any real number. When we square a real number, we get a number that's not negative. So x squared is either positive or 0. And so the principal square root of x squared is the absolute value of x. Okay, a real number x can be positive, negative, or 0. If x is less than 0, then x squared is greater than 0. We know that from experience. If you have a negative number and square it, you get a positive number. And so the principal, or positive square root of x squared, is positive. So we're just reiterating this definition up here. So even if x itself is less than 0, then the principal square root of x squared is equal to the absolute value of x. If we don't include the absolute values, in this case, we're saying that the positive square root of x squared is a negative number if we do not include the absolute values. Okay, when variables are involved, variables with exponents that are multiples of 2 are perfect squares. They're considered perfect squares. And the multiples of 2 are just the even integers. So the first few even positive integers are 2, 4, 6, 8, 10, and so on. Okay, so if x is a real number, we regard x raised to an exponent that's even as a perfect square. So if the exponent on a variable is even, it's considered a perfect square. And we want to know how to simplify square roots of variable expressions. So as we've already seen, if x is a real number, the square root of x squared is the absolute value of x. Because if we square the absolute value of x, we just get x squared. The square root of x to the 4th is x to the 2nd. Notice that on this one, I'm not using absolute value symbols around x squared. So why aren't they there? If x itself is negative, x squared is positive. So we don't need the absolute value symbols in this case. But for this one, we do. If we want to compute the square root of x to the 6th, we have to write the absolute value of x to the 3rd. Because if x is negative first, x to the 6th is positive. But x to the 3rd, if x is negative, x to the 3rd is negative, so we have to take the absolute value of it. For the square root of x to the 8th, that's equal to x to the 4th. And here we don't need the absolute value symbols because x to the 4th is going to be positive even if x itself is negative. And so on. You can probably see what the pattern is when we need the absolute value symbols and when we don't. Okay, note that, for example, when evaluating the principal square root of x to the 8th, as I've already mentioned, the absolute value symbols are not required to enclose x to the 4th because x to the 4th is already positive even if x itself is negative. But it isn't incorrect. It's not incorrect to use the absolute value symbols for a principal square root or a positive square root, because the absolute value of x to the fourth is equal to x to the fourth. Okay, most of the time, well, when you're working in Newton, just make sure that you read the directions carefully. But much of the time, you're going to be able to assume that x itself is positive so that you won't have to include the absolute value symbols. Okay, that's what we talk about next. Let's assume that x is a positive real number so that the square root of x to the second equals x without the absolute value symbols. So that's what this note in parentheses reiterates. The absolute values aren't required if it is assumed that x is greater than 0. We've seen some examples of how to simplify square roots of perfect squares, but on this one, I'll go into some more detail. Let's consider how to simplify the principal square root of x to the 18th. And we're assuming that x is positive. The index of a square root is n equals 2. Since the exponent 18 is a multiple of 2, divide 18 by 2, which is 9, and then 9 is the exponent on x when the square root of x to the 18th is simplified. So just to reiterate that, the square root, it's understood that the index is 2. The exponent on x is a multiple of 2. So when you simplify this, it becomes x to the 18 divided by the index 2, or x to the 9th. So if you understand that, we can simplify variable expressions with larger even exponents. Suppose we have the square root of x to the 112. What will that simplify to? Yeah, the index is 2 because it's a square root. The exponent on x is even. 112 is even. So when we remove the radical, we get x to the 112 divided by the index 2. But 112 divided by 2 is 56. So this, the square root of x to the 112 simplifies to x to the 56th. This idea of dividing the exponent on the variable that's inside the square root by 2 when you remove the radical, that will be generalized because we not only have to learn about square roots, we have to learn some things about radicals with higher indexes. Okay, that's what we'll discuss next. We will discuss radical signs with higher indexes. Okay, so the next one, the radical sign with index n equals 3 looks like this. We have the radical symbol, and the positive integer 3 is in that little space there. I don't know what we call that. But anyway, if the index is 3, we call that a cube root. So if a is a number, if we let a be a number, then the radical of a with index 3, or the cube root of a, that is equal to the number whose cube is a. So in other words, if the cubed root of a equals m, then that's equivalent to writing a is equal to m to the third. Okay, for cube roots, we want to know what some of the perfect cube whole numbers are. We looked at a list of perfect square whole numbers a few minutes ago. Now we'll focus our attention on perfect cube whole numbers. The perfect cube whole numbers are found by cubing whole numbers. In other words, raising whole numbers to the third power. That's what it means to cube a number. So cube roots of perfect cube whole numbers simplify to whole numbers. So here's an example. The cube root of 8 equals 2 because 2 to the third power equals 8. So we say that 8 is a perfect cube whole number because when we compute the cube root of 8, we get a whole number. So it's a perfect cube. See what I mean? Okay, so being familiar with a bunch of perfect cube whole numbers is going to come in handy. Here's a list. So it's not too hard to remember the perfect cube whole numbers up to 1,000. So 18, 27, 64, 125, 216, 343, 512, 729, and 1,000. Those are perfect cubes. I'll go ahead and write out in a little more detail. 1 is 1 to the third. 8 is 2 to the third. 27 is 3 to the third. 64 is 4 to the third. 125 is 5 to the third. 216, 6 to the third. 743 is 7 to the third. 512 is 8 to the third. 729 is 9 to the third. And one of the easiest ones, 1,000, that's just 10 to the third. 10 times 10 times 10. And that's as far as I'll go. But work on being familiar with these perfect cube whole numbers so that when you see them, you automatically have a reaction on how to simplify a cubed root of a perfect cube. Okay, evaluate or simplify the following cube roots. The cube root of 64, that's equal to 4 because 4 to the third, 4 times 4 times 4 is 64. The cube root of 343, that's equal to 7, because 7 to the third, 7 times 7 times 7 is 343. 343. Hey, what about the cubed root of a negative number? What's the cubed root of negative 125?
The absolute value of 5.
What's that?
Absolute value of 5.
Well, it's going to involve 5 in some way, but not, it won't involve the absolute value. So I got an answer online, which of negative 5, and negative 5 is correct. The cubed root of negative 125. Let's think about the definition. The cubed root of a number is equal to whatever number you would have to raise to the third power in order to get that number. So the number that you would have to raise to the third power to get negative 125 is negative 5, because negative 5 times negative 5 times negative 5 is negative 125. So the cubed root of negative 125 is negative 5. And corresponding to that is negative 5 to the third. Negative 5 times negative 5 times negative 5 is negative 125. Okay, so here's one difference between a square root and a cube root. Remember, the square root of a negative number is not a real number, but the cube root of a negative real number is also a negative real number. Okay, then this one, the cube root of negative 1,000, that's equal to negative 10, because if you cube the number negative 10 times negative 10 times negative 10 is negative 1,000. Hey, when variables are involved, we know that we have a perfect cube if the exponents are multiples of 3. Remember the perfect square variable parts had exponents that are multiples of 2. So the perfect cubes have exponents that are multiples of 3. So here's the first few perfect cubes: x to the third, x to the sixth, x to the ninth, x to the 12th, x to the 15th, x to the 18th, x to the 21st. Each one of those exponents is a multiple of 3. So they are treated as perfect cubes. So when simplifying cube roots of perfect cubes, we follow a similar procedure that we did when we simplified square roots of perfect squares. So the cube root of x to the third is x to the 3 divided by 3, or x to the first. To simplify the cube root of x to the sixth, then we divide the exponent 6 by the index 3, which is 2, so it simplifies to x to the second. To simplify the cube root of x to the ninth, Well, without the radical, we have x, and then the exponent is 9 divided by the index 3. 9 divided by 3 is 3. You see the pattern here. So the cube root of x to the 12th is x to the 12 divided by 3, or x to the 4th, because 12 divided by 3 is 4. So if you see the pattern, you can simplify cubed roots of larger or variable parts with larger exponents that are multiples of 3. What's the cubed root of x to the 99th? Yeah, it's equal to, well, note that 99 is a multiple of 3. 3 times 33 is 99. So the cubed root of x to the 99th simplifies to x to the 99 divided by 3, or x to the 33. Pretty simple, huh? Okay, so in general, if the index of a radical is an even integer, so if the index of a radical is even, like 2, 4, 6, 8, and so on, and the radicand is a negative real number, then it's not a real number. If the index of a radical is an odd integer, like 3, 5, 7, 9, and so on, and the radicand is a negative real number, then it's a negative real number. So does anybody did it occur to you to wonder, what about a radical whose index is 1? You won't find that addressed or mentioned in the textbook, but we could use it. I'll just say in passing, if the index of a radical is 1, it just returns whatever is inside the radical. It's like an identity radical, and since that's all it does, we don't really need to worry about radicals with index 1. So just keep that in mind, but don't worry about it. Okay, a couple of examples based upon the statements above. The square root of negative 64 is not a real number because the index is an even integer 2. So it's okay if you include the index 2 or don't include it, because if you don't include it, it's understood to be a square root. But anyway, the square root of negative 64 is not a real number. But the cubed root of negative 64 is equal to negative 4. This time the index is odd, and a radical whose index is odd and the radicand is negative is equal to a negative real number. And as you've seen, this is consistent with this equation. If you cube the number negative 4, it's equal to negative 64. Okay, along the same lines, the fourth root of negative 81 is not a real number because the index is even. The fifth root, this time the index is odd. The fifth root of negative 7,700 and 76 is equal to negative 6. And that's related to this. If you raise the number negative 6 to the 5th power, you get negative 7,776. So you probably won't see perfect 5th powers that are that big, but this is just an example to illustrate that if the index of a radical is odd and the radicand is negative, then it's equal to a negative real number. Okay, here are 10 problems. I'll give you a few minutes to work those out. Work those out on paper. It shouldn't take too long. Some are easier than others, but yeah, see what you get. We'll compare notes in a couple of minutes. Okay, let's start these. The fourth root of 16. How much is that? That's 2, because 2 to the fourth, 2 times 2 times 2 times 2 is 16. The fourth root of negative 16. It's not a real number. It's a number, just not a real number. So not a real number because the index is even, not a real number. The fifth root of 32 is also 2 because 2 to the fifth power is 32. And the fifth root of negative 32 the fifth root of negative 32, the index is odd, so this is it's going to be equal to a negative real number. In this case, negative 2. Because if you raise the number negative 2 to the fifth, you get negative 32. Keep in mind that parentheses are needed. If this means we're raising the number negative 2 to the fifth. It doesn't mean the same thing as the negative of 2 to the fifth if there are no parentheses. Okay, the sixth root of 729. Yeah, that's 3 because 3 to the sixth is 729. You might remember 729 is also 27 squared. Okay, the sixth root of negative 729. It's not a real number. The index is even, and the radicand is negative. So it is a number, it's just not a real number. So for now, we just identify them as not being real numbers. The seventh root of 78,125. Well, that just turns out to be 5. Because 5 to the seventh power is equal to 78,125. And so the seventh root of negative 78,125, that will be equal to negative 5. The index is odd, and the radicand is negative, so it's equal to a negative real number. And if you raise the number negative 7 or negative 5 to the seventh, you get negative 78,125. Okay, this one, you should know this one. This is one that's worth remembering. The 10th root of 1,024. That's just equal to 2. So 2 to the 10th is equal to 1,024. So knowing that 2 to the 10th equals 1,024, that is considered one of the handy exponential equations to remember. And it corresponds to this radical with index 10. The 10th root of negative 1,024 is not a real number. The index is even, and the radicand is negative, so it's not a real number. Okay, we have a little bit more than a minute left. Here's another word problem. I didn't send this one to you, but we might be able to set it up at least. before it's time to quit. This says find the number of calories in 57 ounces of a drink if there are 48.5 calories for every 9.5 ounces of the drink. So if we let X be the number of calories in 57 ounces, then we can write this. X is to 57 as 48.5 is to 9.5 ounces. So X corresponds to 48.5. Each one of those represents calories. 57 corresponds to 9.5. Those are ounces of drink. So you can write the equation X is to 57 as 48.5 is to 9.5. Okay, that's the setup on that one. That's all we have time for right now. Tomorrow we'll be looking at more material about radicals.